Hello students, and welcome to our lesson on divisibility, factors, and multiples. What we're going to be doing here is breaking numbers down into their prime factorizations. That way we can find GCFs, LCMs, and numbers of factors and what all the factors are. If none of that made sense to you, don't worry, we're about to dive right into it. So first, divisibility rules. A number is divisible by another if it can be divided evenly with zero remainder. So in our essential skills lesson, we talked about how to find remainders using long division. And the idea of divisibility is that when you divide, you get zero remainder. But we don't always want to have to do long division. So we have a couple rules for common numbers where we can check very easily if they are divisible by that number. So we can see our first one here is 2. A number is divisible by 2 if it is even, and even simply means that it ends in a 0, 2, 4, 6, or 8. So if it ends in any of those numbers, then it is divisible by 2, and it is even. Divisible by 3 is if the sum of the digits is divisible by 3. So we'll see a couple examples of that, but remember, sum means to add. So if you add up all the digits and that number is divisible by 3, then the entire number was divisible by 3. A number is divisible by 5 if it ends in a 0 or 5. Nice easy rule there. 9 is exactly the same as 3, just with the number 9 instead. So if the sum of the digits is divisible by 9, then the entire number is divisible by 9. And then 10, if the number ends in a 0, then it is divisible by 10. So now these are just a few quick rules that are very common and fast to use. There is obviously infinitely many more numbers that we could divide by and try to check, but these are the ones that are going to show up the most often, especially 2, 3, and 5 are going to be particularly relevant to us. So the rules for 2, 3, and 5 we're going to use all throughout this lesson. All right, example 1. We want to use these rules to test if 522 is divisible by any of those numbers. So to test for 2, all I have to do is check if this number is even. 522 ends in a 2, and ending in a 2 fits the description of being even, so this number is divisible by 2. So I'm just going to underline the 2, meaning yes. For 3, we have to add up the digits. So if I add 5 plus 2 plus 2, that gives me 9, and 9 is divisible by 3. So because the sum of the digits is divisible by 3, the entire number is divisible by 3. For 5, we check what the number ends in. It's a 2, which does not meet the rule. For 5, it has to end in 0 or 5. So this number is not divisible by 5. And it's also not going to be divisible by 10 for the same reason. To be divisible by 10, you have to end in a 0. So this 2 at the end makes it not divisible by 10. For 9, the rule is the same as 3, just with the 9. We already summed up the digits and got 9. 9 is divisible by 9, and so that means the entire number 522 is divisible by 9. So 522 is divisible by 2, 3, and 9. All of those will work. Next one, 4,215. This number ends in a 5. So because it ends in a 5, that means this is an odd number, so it is not divisible by 2. If we add up these digits, 4 plus 2 plus 1 plus 5, this is going to add up to be 4 plus 2 is 6, plus 1 is 7, plus 5 gives us 12. 12 is divisible by 3, and so this whole number is divisible by 3. 12 is not divisible by 9, so 9 is not going to work. Okay, remember we check the same thing. We check the sum of the digits right here. Since it is divisible by 3, 3 works, but since 12 is not divisible by 9, 9 does not work. All right, the original number ends in a 5, which means that this number is divisible by 5. But for the same reason, because it ends in a 5, it is not divisible by 10. It would have to end in a 0. And so we can see that 4,215 is divisible by both 3 and 5, but none of the other 3 numbers. Okay, so now why do we want to know what a number is divisible by so quick? Well, we want to be able to break numbers down into factors. All right, so factors of a number are whole numbers that can be multiplied together to give you the original number. So we just saw in the previous number 1 here, okay, up here 522 is divisible by 2 and 3. That means that 2 and 3 are both possible factors, okay? Because they will evenly divide this number. So factors are always going to be whole numbers, and they're going to evenly divide the original number. But specifically, when we multiply all of the factors together, we're going to be able to get the original number. All right, so now a prime number is going to be very important to us because a prime number has exactly two factors, and those two factors are just 1 and itself. So for example, the number 2 is prime because the only way you can get 2 is by multiplying 2 by 1. The number 3 is prime, the number 5 is prime. Notice those three numbers are the first three divisibility tests we had. Okay, that's why they're so important. And then we have more. We could go 7, 11, 13, and there's infinitely many more prime numbers as we go along. Hopefully, we're never going to have to think too hard about anything above 11, but realistically, we could use any prime numbers as factors to make new numbers. Okay, every whole number greater than 1 can be written as the product of prime numbers. This is the key to what we're about to be doing. Every number can be broken down into the product of prime numbers. And so what we're going to do is create a prime factorization. And prime factorization is just us breaking down a number into all of its prime factors. And we are going to use this for quite a few things in this course. In this lesson, we'll find greatest common factors and least common multiples. And in the future, we'll use prime factorization to help us simplify and better understand fractions. Okay, so right here, we have what are called factor trees. So one I already have completed for us, and then the other one we're going to complete together. So the first one says to factor 72 using a factor tree. So what we do is we take the original number and we put that on top, and then we break it into two branches. Okay, the two numbers that this 72 breaks into have to multiply together to give us back 72. So notice that if I multiply 9 times 8, I get 72. So the two branches that come out of it have to multiply together to give you that original number. The number 9 on the left then breaks down to be 3 times 3, because notice 3 times 3 is 9. On the right side, the number 8 breaks down to be 2 times 4, and then 4 can be broken down even farther to be 2 times 2. We do not stop until we get to a prime number at the end of the branches. So notice the ends of all these branches here are 3, 3, 2, 2, and 2. Okay, all the other numbers that were in the middle, so the 9, the 8, the 4, and the 72, those are not part of our prime factorization. Those were just steps to get us there. So the only numbers we actually care about are what are at the end of all the branches, and notice they're all prime numbers. Okay, so now the idea here is that 72, our original number, is the product of the 5 numbers that I underlined that are at the end of the branches. So notice we have 1, 2, 3 2s, 1, 2, 3 2s down here. And we had 2 3s, so down here, 2 3s. So I just take all 5 numbers, multiply them together. This does in fact multiply to give you 72, if you want to fact check it. And that form that it's in right now, we saw in lesson 1, right here, this is called expanded form, where we multiply all the numbers out. But then we also have the form we prefer, which is right next to it, 2 to the power 3 times 3 to the power 2. This is exponential form. And generally, when we write prime factorizations, we want that exponential form because it's a lot tighter and easier to read. All right, we're going to break down the number 120 now using a factor tree. I have a couple placeholders filled in. That way we all do it the same way. So 120 breaks down into 10 times something. So if I divide 120 by 10, I get 12. So 12 is my branch on the right. Then on the left side, we're going to break down 10. 10 is equal to 5 times something. 10 divided by 5 is 2, so I put a 2 there on the left. On the right side, we break down 12 to be 2 times something. 12 divided by 2 is 6, so 2 times 6 gives me that 12. And then one more branch, if we go one step further, 6 breaks down to be 3 times 2. And so the ends of all these branches are what we want to actually take with us. So a 2, a 5, another 2, a 3, and another 2. So then I just copy all these down. So 120 is equal to 3 2s multiplied together, 1 3, and 1 5. If I write that in exponential form, that is 2 to the power 3 times 3 to the power 1, where I don't need to write the 1 because the 1 doesn't change anything. and then times 5 also to the power 1. Okay, so now we're going to use this in every problem moving forward, so let's get to it. We have two things we really care about here, GCF and LCM, and both are found by using the prime factorization. So when we find each of these, what we're going to do is write each number as a product of prime factors first, aka find the prime factorization. And then we have two different things here. GCF is the greatest common factor. Okay, GCF, greatest common factor. That is the biggest number that divides both numbers. So what we're going to do after we find the prime factorization is we're going to take the highest power of each prime factor that appears in both numbers. So we're going to find, what do both numbers have in common? They both have to have it. Then the other term we have is least common multiple, LCM. And the LCM, or least common multiple, in order to find it, we are going to take the, again, highest power of each prime factor, but this time it's going to be that appears in either number. So instead of them both having to have it, now it's just if one of them has it, it'll go into that least common multiple. And so basically the same process, just in one, we're having to find it in both numbers, and the other, we're finding it in just one number. And to be clear, the least common multiple is the smallest number that is divisible by both of the original numbers. Greatest common factor is the biggest number that divides both numbers. Least common multiple is the smallest number that is divisible by both numbers. All right, let's go ahead and try this example here. So we have the prime factorization of 36 and 60. And so we're just going to go ahead and see the process for finding the GCF and LCM of each. So for the GCF, first thing is notation. When we find the GCF, we are specifically finding the GCF of 36 and 60. And so we write GCF and then in parentheses 36 comma 60. That tells us what we are finding the GCF of. All right. Once we've done that, now we're going to look at the prime factorization, and we want to see what they have in common. So for 36, let's look at the 2's. It has 2 to the power 2, meaning 2 2's. 60 also has 2 to the power 2. So because they both have the same power for 2's, I'm going to take 2 2's with me to the GCF. So I'm going to take 2 to the power 2 down to my GCF. Now we're going to look at the 3's. 36 has 3 to the power 2, but 60 only has 3 to the power 1. So we're going to take the highest power that they both have. So they both have 1 3. 36 has 2 3's, but since 60 only has 1 3, we can say that they both have 1 3. So I'll take 1 3 to my prime factorization. And then for 5's, notice there's a 5 in the 60 prime factorization, but not in the 36. So they do not both have a 5, so I do not bring a 5 with me. All right, now when I simplify this, 2 to the power 2 is 4, times 3 gives me 12. And so 12 is our GCF of 36 and 60. And that means that 12 is the biggest number that divides both 36 and 60. Notice 12 times 3 is 36, and 12 times 5 is 60. So it does in fact divide both numbers. All right, now we're going to find the LCM. The notation is almost exactly the same. We want the LCM and then in parentheses of 36 comma 60. That tells us what we're finding the least common multiple of. And this time we're still going to look at the prime factors, but now we're going to take the highest power that's in either number. So they both have 2 2's still. That didn't change, so we're going to take both 2's. But for 3's, since this 36 has 2 3's and this 60 only has 1 3, we want to take the higher power. So we're going to take 2 3's into our prime factorization. So 3 squared. And then for 5, even though 36 does not have a 5, 60 does. So we want to take the most 5's that we see in either number. And so 1 5 is what we're going to take. So 5 to the power 1. When we multiply all those numbers out, 2 squared is 4, 3 squared is 9, so 4 times 9 is 36, and then times 5 is going to give us 180. So our least common multiple of 36 and 60 is 180. And that means that 180 is the smallest number that is divisible by both 36 and 60. All right, number 3. Now we're going to do the exact same thing, but we're going to do it from scratch. So we're going to use prime factorization to find the GCF of 48 and 72. In order to do this, I need to break each of these numbers down. So I'm going to start by breaking down 48. And the way I do it is I start with the smallest number that I know divides it, and then I break it into two branches. So the smallest number that I know divides 48 is 2, because it's an even number, so I know it's divisible by 2. And 48 divided by 2 is 24. Now I choose the smallest number because this means that my 2 branch is done. I don't have to worry about it anymore. It's already prime. But for the 24 branch, I have to keep going. 24 is divisible by 2, and that gives me 12. 12 is divisible by 2, and that gives me 6. 6 is divisible by 2, and that gives me 3. So altogether, we have that 48 is 2 times 2 times 2 times 2 times 3. Okay, we're going to do the same thing for 72. 72 is divisible by 2 and gives us 36. 36 divided by 2 gives me 18. 18 divided by 2 gives me 9. And 9 is not divisible by 2, but it is divisible by 3, and it leaves me with a 3. So I have 3 2's and 2 3's. So now we could take these trees and write them into their prime factorizations in exponential form, like what we had up here at the top, but we don't actually have to because we can see all the 2's there. So we can go ahead now and just answer the question. The GCF of 48 and 72 is going to be equal to, we want to take the most 2's that they both have. So this 48 has 4 2's, but 72 only has 3 2's. So I can only take 3 2's to my prime factorization. So I'm going to take 2 to the power 3. Then for 3's, 48 has 1 3, 72 has 2 3's. So I take the biggest number of 3's that they both have, which is just 1. Okay, so we're going to take 3 to the power 1, which is just 3. Then if we multiply that out, 2 cubed is 8 times 3 gives us 24. And so 24 is the GCF of 48 and 72. All right, we're going to do the same thing now for finding the LCM in number 4 of 18 and 30. So we're going to break down 18 to be 2 times 9, and 9 is 3 times 3. And we'll break down 30 to be 2 times 15, and then 15 is 5 times 3. So now if we want to find the least common multiple, or the LCM, of 18 and 30, we just look at each factor and take the most of each thing that we see. So both numbers have 1, 2, so 1, 2 is the most we can take. 18 has 2 3's, but 30 only has 1 3. So because we're doing the least common multiple, we take the higher number of 3's. So we're going to take 2 3's. So 3 to the power 2. And then there's only 1 5. It shows up under the 30, so we're only going to take 1 5. If we multiply all this out, 2 times 3 squared times 5 gives us 90. And so 90 is the smallest number that is divisible by both 18 and 30. All right, a couple quick applications of why we care about this. So sometimes you might want to find squares to fit certain situations. In this case, we're going to be talking about tiling a floor and how to choose the best size tiles. So it says a rectangular floor is 84 inches long and 108 inches wide. The floor will be tiled with square tiles of the largest possible size that require no cutting, meaning no remainder on each side. We want to use prime factorization to find the side length of each square tile. So what we are actually trying to do is we're trying to find the biggest number that divides both 84 and 108, meaning we are trying to find the GCF of 84 and 108. Okay, what this is going to look like, well, we're trying to tile a rectangular floor that is 84 on the other side, 84 by 108. And so we're trying to put in all these square tiles going across like this, where when we get to the end of the wall, we fit perfectly and don't have to cut any tiles. But we also need it to fit vertically, so we can tile it in both directions without having to cut any of these tiles. So we need the size of the tile to evenly divide the side length, but that has to be true on both side lengths. So what we're going to do is just like before, we are going to break down each of these numbers into prime factorization. So we'll start with 84. 84 is 2 times 42. 42 is 2 times 21. And 21 is 3 times 7. If we do the same thing for 108, We have 2 times 54. 54 is 2 times 27. 27 is 3 times 9. And 9 is 3 times 3. So now when we find the GCF, all we have to do is take the things they have in common. So they both have two 2's. So I will take 2 to the power 2. 84 has 1 3. 108 has 3 3's. So the biggest number of 3's they both have is just 1. So we're only going to take 1 3. And although there's a 7 over here in 84's prime factorization, there is no 7's in 108's. So we do not take any 7's. Okay, when we multiply out 2 squared times 3, this gives us 12. And so we need 12 by 12 inch tiles. And what we're really doing here is saying that if we buy 12 by 12 inch tiles, we will be able to tile across this side that is 108 inches long and up this side that's 84 inches long, and we will have nothing left over. It'll take 9 tiles to go across the long way and 7 tiles to go across the short way. All right, number 6, application of LCM. It says 2 traffic lights blink at different intervals, one every 40 seconds and the other every 50 seconds. Use prime factorization to find when they will blink together. So we want to find out after how many seconds will they blink at the same time, meaning we want to find the smallest number that is divisible by both 40 and 50. So we are actually finding the LCM of 40 and 50. Okay, so in order to do this, just like before, we're going to break down the two numbers. 40 is 2 times 20, 20 is 2 times 10, and 10 is 2 times 5. If I do the same thing for 50, we have 2 times 25, and then 25 is 5 times 5. So when we find the LCM, we want the biggest number of 2's we can grab. So 40 has 3 2's, so I'm going to bring 3 2's. And then 50 has 2 5's, so I'm going to bring 2 5's, 5 to the power 2. But those are the only prime factors I can bring with me. Okay, no other numbers there. If we multiply this out, 2 cubed is 8, 5 squared is 25, 8 times 25 gives me 200, and we are talking about a number of seconds here. So after 200 seconds, both of these traffic lights will be blinking at the exact same time. All right, we just have a little bit more to get through with prime factorization, and now we're going to talk about finding all of the factors of a number. So we were just finding all the prime factors, but not every factor is prime, okay? Because factors can be combinations of prime factors. So for example, in the last number, we saw that 40 is 2 times 2 times 2 times 5. But we also saw that 40 is 2 times 20 right here. So 2 and 20 are both factors of 40. Okay, even though they're not both prime, 20 is not prime, it is still a factor of 40 because 2 times 20, these are whole numbers that multiply together to give us 40. So what we're going to do is take the prime factors down here, 2 times 2 times 5, and put them together in every possible combination. And there's a very systematic way to do this. So once we know the prime factorization of a number n, we can generate all of its factors by using the prime factorization. So if we have a prime factorization that is generally written as a number to the power a1, a number to the power a2, and then dot, 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 a number to the power ak, then the total number of factors is going to be these exponents, each plus 1, and then multiplied together. Okay, so for example, we have that 12 is equal to 2 squared times 3. Okay, we've seen that previously. So 2 squared times 3, if I want to know how many factors 12 has, what I'm going to do is take the 2 and the invisible 1 that's over the 3, and I'm going to plug them into this formula. 2 plus 1 times 1 plus 1, where again, I'm taking this exponent and putting it here, this exponent putting it here, and just adding 1 to each of them. Okay, 2 plus 1 is 3, 1 plus 1 is 2, so 3 times 2 gives me 6. So 12 has 6 possible factors just by taking the exponents from the prime factorization. Right, and then if we want to actually list all of the factors, so all 6 of them for 12, what we do is we take different powers of each prime and multiply them together. So we're going to see an example that's pretty big with the number 120 here. So we want to find the number of factors 120 has and then list all of them out. So the first thing I'm going to do is break down 120 to prime factors. We have 2 times 60. 60 is 2 times 30. 30 is 3. Well, let's keep going with 2's. We'll go 2 times 15. 15 is 3 times 5, and we're done. So we can say that 120 is equal to 2 cubed times 3 times 5. And if I haven't used this notation yet, by the way, these dots right here represent multiplication. We'll see that a lot more in the future. All right, so we have 2 cubed times 3 times 5. So if I want to find out the number of factors, so number of factors, all I have to do is take each of the exponents, so 3, 1, and 1, and just plug them into the formula. So we're going to have 3 plus 1 times 1 plus 1 times 1 plus 1. And if we multiply all that out, we have 4 times 2 times 2, which is going to give us 16 possible factors. Okay, so again, I'm just taking the exponent of 3, putting it right here, taking the exponents of 1, and putting each of them into the formula. All right, so now let's go find all 16. To help us find what all the factors of 120 are, we're going to use what's called a tree diagram. And what we have to understand to start off is that what we're actually doing is taking each prime factor, so let's look at 2 to the power 3 to start, and we are putting together every combination of exponents. So for the prime factor of 2, it has an exponent of 3. So all of the possible ways we could include that prime factor of 2 is by doing 2 to the power 0, 2 to the power 1, 2 to the power 2, or 2 to the power 3. Now let's connect a couple dots here. Remember, we added together the exponent of 3 plus 1, and that gave us the number 4 earlier. The reason we were doing that is that this number 3 up here, this exponent, tells us most of the possibilities for 2, but it leaves off 2 to the power 0. So notice, when I write out all the ways I can include 2, I could have all 3 2's in there, I could have 2 of the 2's in there, I could have 1 of the 2's in there, or the extra option is that I could have none of the 2's, and that's what 2 to the power 0 represents. So the reason to count all the number of factors, we add 1 to each exponent, is to account for the fact that we could include 0 of that prime factor. And we need that information because otherwise we're going to be missing half of the possibilities. Okay, if we leave off the fact that we could have 3 to the 0 or 5 to the 0, that is going to way trim down our number of factors, and we are not going to get to this number 16. But okay, watch what happens next. We're going to create a tree now. So these starting places are where we are on the tree. Then we're going to break each of those spots into 2 branches. Okay, 2 branches coming out of each prime factor of 2. The reason we're breaking it into 2 branches is because our next prime factor is the number 3, and 3 is 3 to the power 1 in that prime factorization. So all of the possible ways we could include that number 3 are either including it 0 times or including it 1 time. Okay, so just like for the number 2, because we had 2 to the power 3, that meant we could have 3 2's, 2 2's, 1 2, or 0 2's. Same thing for the prime factor of 3. We can either have 1 3 or we could have 0 3's. And those are both possibilities. So now it becomes very easy from here because we're just going to copy and paste what we just did. So 3 to the power 0 and 3 to the power 1 in the next section, 3 to the power 0 and 3 to the power 1 again, and one more time. All right, so we've accounted for the 2's and we've accounted for the 3's, but now we got to account for the 5's. We have 5 to the power 1 in our prime factorization, so just like I did with 3, I'm going to break each branch I have into 2 new branches. So coming out of every red 3 that I just wrote down, 2 new branches. And exactly the same way I did with 3, because we have 5 to the power 1 in our prime factorization, the 2 possibilities are to either have 0 5's included or to have 1 5 included. So from each branch, I'm splitting it into 2 new branches that either has 5 to the 0 or 5 to the 1. So in every single one of these places, 5 to the 0 or 5 to the 1. 5 to the 0, 5 to the 1, 5 to the 0, 5 to the 1. over and over and over again. Very tedious, hopefully you're realizing. But okay, that is all of the setup we need. Our tree diagram is created. Now all we have to do is multiply along the branches. So before we do that, I want to point out, notice that at the bottom of this tree diagram, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and 16 ends to those branches. And we were expecting 16 factors. So the way this tree diagram works is we multiply along each direction of the branches. So for the first branch, I'm going to take 2 to the power 0, multiply by 3 to the power 0, and then by 5 to the power 0. Notice those are just going along this outer left route. When I multiply all those together, each of those things to the power 0 equals 1. Okay, everything to the power 0 is just 1. So 2 to the power 0 is 1, times 3 to the power 0 is 1, times 5 to the power 0. I just get 1 at the bottom of that thing. Now let's do the far other side so we can see the other extreme. If I multiply all the branches on the right side, I have 2 cubed on top. Then I follow the branch to 3 to the power 1, follow the branch again to 5 to the power 1. This outermost branch system is 2 cubed times 3 times 1. Well, 2 cubed is 8, and 3 to the 1 and 5 to the 1 are just 3 and 5 respectively. So I have 8 times 3 times 5. That equals 120. So on the far left, we have the smallest possible factor, which is 1. And on the far right, we have the biggest possible factor, which is 120. Every other factor is going to show up between these two ends of the branches. So all we have to do is follow the branches for each new one. So I'm going to delete some of my highlighting here so we can follow the next branch. For the second from the left branch, what we have is 2 to the power 0 on top times 3 to the power 0. So we started off the same as our first one, but instead of continuing down to 5 to the power 0, I'm going to turn right now and go to this 5 to the power 1 branch. When I multiply those numbers, 2 to the 0 times 3 to the 0, that's just 1. But then times 5 gives me 5 at the bottom. Okay. Then I move on to a new branch. So let me delete my highlighting. I'm only going to highlight one more, and then we'll do these without all the highlighting. So one more branch to the side. We have 2 to the 0 times 3 to the 1. And then if I go left on the green fork, 5 to the 0. 2 to the 0 and 5 to the 0 are both just 1, but 3 to the power 1 is 3. So when I multiply these all together, I get 3. Okay. If we go one spot to the side, I'm going to have 2 to the power 0 times 3 to the power 1 times 5 to the power 1. That works out to just be 3 times 5, which is 15. And I'm going to throw some commas in here just in case it gets a little crowded. Now we're just going to go through each branch the rest of the way. So after the 15, I have 2 to the 1 times 3 to the 0 times 5 to the 0. That's just 2. Then I have 2 to the 1 times 3 to the 0 times 5 to the 1. That's 10. Then 2 to the 1 times 3 to the 1 times 5 to the 0. That is 6. 2 to the 1 times 3 to the 1 times 5 to the 1. That's 6 times 5, which is 30. Then we have 2 squared, 3 to the 0, 5 to the 0. That is just 4. 2 squared, 3 to the 0, 5 to the 1. That is 20. 2 squared, 3 to the 1, 5 to the 0. That is 12. 2 squared, 3 to the 1, 5 to the 1. That is 60. 2 cubed, 3 to the 0, 5 to the 0. That is just 2 cubed, which is 8. Then 2 cubed, 3 to the 0, 5 to the 1. That is 40. 2 cubed, 3 to the 1. That is 24. And then our last one over there was 120. So if you go across the bottom, you'll notice none of them are the same. And we have all 16 factors. So these pink numbers down here is every single whole number that divides 120. That's it. There's no other numbers. 120 has 119 numbers that are less than it, but only 16 actually work out to divide 120. And we just found all of them. Great job, team. Okay, last thing we're going to talk about is the connection between the GCF and the LCM. So for any two numbers a and b, this following relationship holds that the GCF of a and b multiplied by the LCM of a and b is equal to just a times b itself. All right, so we're going to verify this rule real quick for 18 and 24. So what we're going to do is find the GCF and LCM, multiply them together, and show that it's the same as 18 times 24. So on the side, real quick, we'll break these down. 18 is 2 times 9, 9 is 3 times 3. 24 is 2 times 12, and 12 is 3 times 4, which is then 2 times 2. So if we find the GCF of these numbers, they both have a 2 and they both have a 3. So our GCF is going to be 2 times 3. For the LCM, the most 2's I see is 24 has 3 2's, so 2 cubed. 18 has 2 3's, so 3 squared. And that catches all of our factors. So we have a GCF of 2 times 3, which is 6. An LCM of 2 cubed times 3 squared, which is 8 times 9, so that's 72. And so we want to check, is 6 times 72 equal to 18 times 24, which is the original two numbers multiplied together? So if we multiply out 6 times 72, that is 432. And if we multiply out 18 by 24, that is also 432. And so we have just shown, by these two being the same, that the GCF and LCM multiplied together give us the same thing as multiplying the original two numbers. All right, that's all I got for you guys in this one. Remember, prime factorization is going to be especially important when we get to fractions and we want to reduce fractions. So make sure you're practicing that prime factorization. See you guys in the next one.